Welcome to Communication Electronic Assignments video presentations. Our topic of our project is Aquarium Remote Controlled Cooling and Lighting System, presented by myself, Ian Tai, and my partner, Khairul Ikwan. The block diagram of our project would be frequency synthesizer, transmitter, receiver, frequency to voltage converter, and finally fan speed and LED brightness. Without further ado, let's dive in to the simulation.
Now, we will be showing the working of the oscillator for our PLL circuit. For this oscillator, we will be using the 555 IC. The 555 timer IC is a very cheap, popular, and useful precision timing device which can act as either a simple timer to generate single pulses or long time delays, or as a relaxation oscillator producing a string of stabilized waveforms of varying duty cycles from 50 to 100%. We will be using the monostable 555 timer circuit. The formula to find the exact frequency desired are shown here. We will try to get a signal around 100 kHz using a fixed C1 value. We will vary R1 and R2 through the calculation to get their precise value. This 100 kHz will be the input to our PLL.
Moving on to the PLL circuit. The IC used for the PLL circuit is 74HC4046. The value of R1 and R2 as well as C1 is obtained through the datasheet. The low-pass filter used are shown here. It is extremely hard to get the desired VCO range through the datasheet, so approximation is used. We will be using the oscilloscope to monitor the input signal as well as the output frequency waveform. After finishing the circuit, we will run the circuit and turn the signal generator frequency value up and down to observe if our PLL is working fine. And everything is working fine here. Now we will need to find the log range of the PLL. First, we turn the signal generator to around 400 kHz, where the PLL able to log very fast and very stable. Now we turn the signal generator frequency up little by little and observe if the output waveform is locked to the input signal. We need to be a little patient here, as the tracking and capturing in simulation time is not the same as real world time. At around 510 kHz, the PLL is no longer locked. Now we will decrease the signal generator waveform down slowly. Through observation, the PLL no longer locked to the input signal at around 100 kHz. Before moving on to find the capture range, we first need to find the free running frequency. Oddly, our free running frequency of the VCO is around 160 kHz. Now to find the capture range, we will start at 330 kHz. In order to find the capture range, we need to put a signal input at a certain frequency value and then run the simulation, observe and stop the simulation. Before moving to the next incremented signal input, we will debug and reset any data on the microprocessor on the schematic. This is to make sure that the circuit is disconnected and connect back. The incremented value and result are shown here. We will also do the same, just decrement signal frequency from 300 kHz to find minimum capture range. Our capture range are from 250 kHz to 430 kHz. And we are done for the PLL part.
To synthesize frequency from PLL, as the topic suggested, we will first need a frequency divider. The IC used for this is a programmable counter 4017. 4017 gave the option to divide the input signal from 1 all the way to 9. Instead of the modulo N, a rotating switch is used here. This serves as a button that will vary from division of 2 3, 4, and 5. Now, we will connect this frequency divider to our PLL. Ultimately, when the divided signal is connected back to the phase comparator in our PLL, we will get multiply of 2, 3, 4, and 5 of our input signals. As suggested earlier, our oscilloscope output will be 100 kHz. Therefore, we will be able to synthesize 200 kHz, 300 kHz, 400 kHz, as well as 500 kHz. Unfortunately, the 500 kHz signal is unstable, so we will only take the first 3 input.
And we are basically done with our main hero, the frequency synthesizer. Moving on to the application part, we will be using RF module. We will find the TX and RX module in Proteus from Mr. Google and put it in our library. Before moving on, we will need to test if our RF module is working. Decoder and encoder will play some role here. 4 buttons will be connected via logic state on transmitter encoder, which will correspond to the 4 LED at the receiver part at decoder. When logic state 1 at transmitter is given at encoder, LED 1 then will light on after the data is decoded. Test all button and LED and observe if the LED is switched on. All data is transmitted successfully, so all good with our RF module. And we will now connect our frequency synthesizer to this RF module. To be exact, it will be connected at the transmitter, and the synthesizer 200 kHz, 300 kHz, and 400 kHz will be transmitted. To check if this frequency is successfully transmitted, an oscilloscope we use to observe the waveform received at the receiver part and compare it to our waveform before this. This entire circuit will act as a remote control, where data is sent to the receiver and used for the applications.
To be able to use this synthesized frequency, we will need a frequency to voltage converter. So, the LM2907 frequency to voltage IC is used. Voltmeter will be connected as the output to read the voltage and make sure the circuit is running. When we will then input the 3 synthesized frequency and observe the output voltage. However, we are unable to get the suggested input range for the LM2907, which is all the way until 5 MHz. Instead, we only get a range of 1 kHz. Therefore, we will divide the synthesized frequency by 7 to 9 to get the frequency down under 1 kHz. The reliable 4017 divider is used and cascaded 3 times for this. We will then get the voltage 2.15 volt, 3 volt, and 3.9 volt for 200 kHz, 300 kHz, 400 kHz, and respectively.
With the 3 different voltages in our hand, we will then be able to control our fan speed as well as brightness of our RGB LED lamp. To simulate this in Proteus, we'll use 4 different LEDs and connect it to a 5 volt supply. Then we'll connect potentiometer at the input. By adjusting the potentiometer, we can supply 3 different volts, thus resulting the 3 different LEDs brightness. For 2.15 volt, the LED will be the dimmest and the fan speed will be the slowest. 3 volt will be the middle ground and 3.9 volt will give the brightest LED and fastest fan speed. The improvements that we would like to make in our simulation, in our designs, is to have an automated temperature sensor that controls the fan speed, and as well as to have more options in terms of frequencies that is being synthesized. That's all for today. Thank you for watching and staying with us.